Hello, this video is going to be about rate laws. Let's get started. So rate laws, they are going to tell you how fast a reaction can go based on the concentration and the temperature, really. So what we're going to actually do, I'm going to kind of show you how to create a rate law and then kind of talk to you about what a rate law kind of means. And I think by the end of it, you'll really kind of get an idea of what it is. But when we're thinking about data, like take a look at this data table here. If we look at it here, we've got the concentrations of the two different reactants. Here's my equation. It's going to make two different products, but we're not really concerned about that part. And they were able to actually tell how fast the reaction is using some sort of method. Molarity per second is what we're getting in the units, and both of those concentrations are in molarity. Now, if we take a look closely at the data, take a look at this one. This is where the reactant concentration of NO2 is going to be the same each time. But if we look at the concentration of NH4, do you see how it doubled? It went from 0.01 to 0.02. That's twice as concentrated. And if we look over here at the rate, this is twice as fast. Now I know we got this 10 to the 7th sort of thing here, but since they're the same number, I really kind of don't even look at it myself. And so what I'm thinking in my head is, what is 10.8 divided by 5.4? 10.8 divided by 5.4. And you can bust out your calculator or not, but that's going to get you 2. So that means that the rate is going twice as fast when the concentration is doubled. That kind of makes sense, right? Put twice the amount of stuff in there, you get twice the rate. So what we're going to actually do is create this mathematical relationship between rate and concentrations of things, the concentrations of the two reactants. I've got NH4 plus and I've got NO2 1 minus. Oops, that 1 minus should go right in there. And so far what I know is that when I double the concentration of NH4, I will double the rate. And if you look at my mathematical relationship right there, if I say this is 1, then the rate will come out to be 1. But if I double the concentration to 2, then my rate will be double that, or to 2. So far my mathematical relationship that I've got written out here is working. It's looking pretty good. Now I've got to look at my other one, my other reactant. So let's look at NO2. I'm going to have my concentration of the other guy stay the same. And down in here is it's really staying the same, like right here. Let's see it's staying the same. But in that same case, when I look at my other reactant, I can see that it's doubled here. And when I take a look at the rate over on this side, I can see, I'm thinking in my head, 21.6 divided by 10.8. When I think about those two numbers, I can see that it's also doubled. So my rate has doubled. That means, again, that my rate is completely dependent on the concentration of NO2. I can see if my NO2 concentration is 1, my rate will be 1 per se. If I double my rate of NO2, I'll double my rate. So right now, this mathematical relationship looks awesome. And this would be a rate law. The only thing we're missing in there is a constant. That's going to be K. We'll talk about what K is in a little bit, but all of our rate laws are always going to have a constant, and it's specific for each of the actual equations times the concentrations, but they're going to get a little trickier because we might have a different power up here. Let's bring it on down. Sometimes when you look at the data here, again, it's going to have that same formula. Rate equals K times the concentration of our reactants. So I've got this reactant right here. That's a doozy, isn't it? And then my other one is OH minus. And what I'm trying to figure out is how are they actually related? So let's go back to the data here. I can see that these are staying the same. And I am going to double this concentration. So I'm doubling this concentration right here. And I can see that the rate, it does nothing. Which means I could double it, quadruple it, quadrillion the concentration of OH, but the rate will always stay the same. Which means up here, I'm going to have a 0 up at the top. Because that means if I do anything, like if I take 4 to the 0, that equals 1, or 2 to the 0, that equals 1. What this is basically saying is no matter what the concentration of my OH is, it's going to be to the 0 power because it doesn't even relate to it. It won't cause any change in the rate, which really the best way to do it, instead of saying it's a 0 power, you just can take it out entirely because the OH concentration doesn't control it anyway. Now, I don't know about this one, because my whole point of this part was to show you that sometimes reactions don't actually change when the concentration changes. It all depends. So going into a general idea of rate laws, the rate laws are going to tell you how fast a reaction can actually happen. And the first thing that we've got to, I guess the next thing we're going to talk about is the different kind of orders. So this reaction, since there's like a microscopic kind of 1 right there, there's a mini 1. This is first order in relationship to NH4. There's a mini 1 right there too. You could have it or not, and that means it's first order for NO2. The overall rate law, or the overall order, is going to be 1 plus 1, or 2. You just add up all those numbers, the 1 and the 1, to make 2. Let's do a practice problem right here. All right, the experimentally determined rate law for the reaction. Here's the reaction. At this point, it's really not that useful to us. It's just a reaction. But the rate law is important. It says, what are the reaction orders of this rate law? So that would mean it is second order for NO. And I know that because it's got that mini 2 right there. And I would say it's first order for H2 because there's a mini 1 there. And then overall, it's going to be a third order reaction because 2 plus 1 makes 3. That would be my answer to number 1. All right, looking at B. It says, does doubling the concentration of NO have the same effect on the rate as doubling the concentration of H2? Let me bring down the rate law here a little bit better. What it's saying is, if I'm going to double the concentration of H2, if this was 1 and then it's going to become 2, what I'm doing to the rate is, it was 1 when the concentration is 1, but then when I double it, it becomes 2. So every time I double it, it becomes twice as fast. Does that same thing kind of happen when I'm looking at NO? If NO is 1, 1 to the second, 1 to the second is 1, so my rate law would be 1. Well, what if I make the concentration of NO 2? Now I've got 2 to the second. That won't just make it twice as fast, it'll make it 4 times faster. So the order of the reaction actually tells us how fast a reaction will go depending on what you do to the concentration. So my answer to B would be no. Doubling one does not have the same effect as doubling the other because they are different orders of reaction. One's a first order and one's a second order. So one will double, but the other one will quadruple if you double the concentration. All right, another thing to know is you're only going to be able to get the rate law when you're getting data. So if you look at this equation, you might be like, oh, that's the reactant. This should be a 2 there because there's a 2 here. It doesn't work that way. Same as this one. Look at, there's a halvesy. There's no halvesy in balance equations. So you can only get it through actual data, which is what our charts are all about. All right, let's go to this one. This was the first one we did at the very beginning of this. And now we've got our rate law, which is something we came up with. What I want to solve for is K now, which basically means pick any lane you want, any lane at all. You could take this lane, all of reaction 1, experiment 1, or 6. It really doesn't matter. I'm going to take 3 just because I feel like it. And I'm going to plug in the numbers. In other words, the concentration of NH4 is 0.004. This is 0.04. My NO2 is 0.2. I want to solve for K, and they tell me my rate is this number, 21.5 times 10 to the negative 7. So really what I'm going to do in my calculator is take these and divide it out. So I'll do 21.5 e to the negative 7. Divide that by 0.04, get a number, and then divide that number by 0.2. My calculator spits out 2.6, I'll go 2.69 times 10 to the negative 4. That's my K value, that's my constant. Every single reaction has a different K value, and we can use the data to find that. The only thing that's kind of tricky is solving for the units. Now my rate is in molarity per second, and these two are in molarities. So if I just look at the units of this, molarity per second equals K times molarity, molarity. If I'm going to solve for K, I'm going to divide both sides by molarity. And these cancel too. And then I'll divide the other side by molarity again to get rid of that one. So really my K has units of molarities on the bottom and seconds on the bottom. If you didn't quite get that one, that's okay. I saw that the textbook doesn't really care too much about that. So maybe if you don't get that, I would just say be okay with it. All right. I've got one problem to kind of sum it all up. Maybe you want to pause it, see if you can do it yourself, and then come back and see what I say about it. That's up to you. Here we go. So I've got my data down below, and I'm trying to find the rate law. Here's my generic equation. So when I find the rate law, I'm going to write out the generic part. Rate equals K times A times B. And I'm going to try to figure out what those exponents are, which the power it is. So first I'll look at A. In order to find the rate law of A, I've got to keep everything else the same. So I'm going to keep B's the same. See how those are samesies? So now I can see that A doubles. When I want to figure out A, keep everything else the same. I'm going to see A doubles, and that means what happens to my rate. So when I'm doing this, I'm thinking to myself, okay, what's 16 divided by 4? Because it's 16 now, and it was 4 before. 16 divided by 4 is 4. So I've got this number 4. And that 4 came out because I doubled it. Now, this isn't a double situation, because I'm thinking 2 to the what equals 4. If I do twice as high the concentration, what power will I need in order to get 4? The power I need, 2 to the 2, is 4. So this is a second order, according to A. All right, I'm going to erase it so I can see my... Now I'm going to go for B. When I'm looking at B, trying to find the coefficient for B, I have to keep A the same. Here we go. We'll keep him the same. And my B has to double, or do triple, or something. Usually it's double. And then I can see that the reaction rate stayed the same, which tells me that it doesn't depend on the concentration of B at all, which means B has to be a 0 up here. Or in other words, I could just take it out entirely. If the rate doesn't change when the concentration changes, I really don't need it at all. This would be my rate law. To solve for my rate constant, I just want to take any lane and kind of just plug and chug numbers in there. So I'll just take lane 1 because that seems like a good enough one to me. So my rate is equal to K times A squared. My rate is 4 times 10 to the negative 5. My K, I got to solve for that, and my A is 0.1 squared. So now I'm going to push buttons on my calculator. Do 4 to the negative 5 divided by 0.1 squared, and my K is 0.004. Unit-wise, here again I'm looking at molarities per second equals K times molarity squared, because that molarity is at 0.1. So I'm going to divide both sides by molarity squared. The O's cancel out. This top molarity cancels out, but there's still one left on the bottom. So my units again are molarity times second on the bottom. That's my rate constant. So then you might be thinking, part C, what would be the rate of the reaction if you put in this and this? Well, in that case, I'm going to do it right down here. My rate, that's what I want to solve, is equal to K, now I actually have a number for that, 0.004, times my A squared. And my A in this case is 0.05. My B doesn't matter, so I'm just not going to include it. I can figure out how fast that rate of the reaction is going to be by calculating that. It will be 1 times 10 to the negative 5 molarity per second. That's how fast it'll be. So that's what makes the rate law useful. You can figure out how fast it'll be just by knowing the rate law and being able to plug in the numbers that you want to put in. Last but not least here, what I've got on the syllabus here is a practice worksheet, and it's got a couple of them on there. The third one is really kind of tricky, so if you want a challenge, go for that. If you don't want to do the practice worksheet, totally fine. I've got my answers there posted. Helpful? Maybe, maybe not. That's totally up to you. All right. Have a good night.